There are two main types of fluid flow problems in engineering. The first type does not have any kind of pumps, no frictional lines, no fittings, nothing like that. And so that simplifies our balance a little bit in terms of how we see fluid flow from point 1 to point 2. The second type of problem does include pumps, it includes friction, and you can use a wide variety of liquids in this particular energy balance because you are not neglecting friction and you are using a pump to move the liquid from point 1 to point 2. And that second type of problem is what we're going to be talking about in this particular video. Now, if I go through and solve a full energy balance on a fluid flow system, that's going to be a rather long video, so I've split this video into several parts. In this first part of the video, we're going to draw our diagram and get our energy balance set up, but we are not going to plug any numbers in. Let's take a look at what this particular energy balance might look like in a word problem. Here's a sample fluid flow problem. In this problem, we have a thin sugar syrup flowing from a storage tank to a processing unit. Now, if we look at just a syrup, that viscosity is pretty low, so we could use Bernoulli, but now we know we can't use Bernoulli because we've got a pump. And we also, if we go further into the problem, we've got some valves and some elbows. And because we have that pump, because we have fittings in the line, we know we can't use Bernoulli because Bernoulli does not account for those particular things. So we need to use a full energy balance. If we look at the last sentence of the problem, we're being asked to find the brake power of the pump. Now, the brake power is just the actual power that the pump needs given the inefficiencies of the pump. So if you plug that pump into the wall, that's how much power you need to make that pump run correctly under the process. The first thing we're going to do here is draw the diagram of our process. And in fluid flow problems, drawing the diagram is really critical because it helps you set up your balance correctly. If you do not set up your balance correctly, then you get an incorrect number for your pump energy, and therefore you get an incorrect number for your pump power. And if you do this in an industrial setting and you get the wrong pump power, well, you could end up ordering a pump that's too large or too small. And so if it's too large, you end up with a cavitating pump, which will damage your pump. Or if it's too small, your pump will not be able to handle the flow rate you want, and therefore you're going to have problems downstream with not enough product getting delivered in the time you want it. So we need to start with that diagram. Let's do that. All right, we are going to start with our storage tank. And I am going to put point 1 at the top of the storage tank. And this is because we are given information about what's going on at the top of our tank. We see here that the liquid level in the storage tank is held constant at 2 meters above the entrance to the processing unit. Because the liquid level in the storage tank is held constant, that gives us information about that particular point in the storage tank. And since the process starts at the storage tank and ends at the processing unit, the storage tank needs to be point 1, and the processing unit needs to be point 2. So since we know that processing unit is a little bit below our storage tank, let's draw it a little bit lower than the storage tank. Now we need to connect our storage tank and our processing unit. And if you wonder why I drew that line all wiggly like that, it's because we have 3 elbows that we need to account for. So I will draw the elbows in so we can see exactly where they are, right there. And since we have the connection at the storage tank here, this is where point 2 is. Now we need to put our pump in the line, put it here, and we need to add in a couple of valves. There's our 2 valves for the process. All right, we have our diagram. We've accounted for points 1 and 2. We've got the storage tank, we've got the processing unit, we have our pump, we have our 3 elbows, and we have a couple of valves in the line. We are now ready to set up our full energy balance. And when we write our full energy balance, this is what it looks like. There. So we've got pressure energy, that's our P2 minus P1 term. We've got potential energy, that's our Z2 minus Z1 term. We have kinetic energy, that's our U2 squared minus U1 squared term. And then we have friction energy, which is EF. So let's take a look at those one at a time. First, we'll look at the pressure energy, and we'll see if we can cancel out anything there. In the problem, we're given that the pressure in the processing unit is 15 kilopascals above the pressure in the holding tank. We're not given that any pressure is zero, and we're not given that the pressures are the same. So we need to leave this term the way it is. Now let's look at our potential energy term. We are told that the liquid level in the storage tank is held constant at 2 meters above the entrance to the processing unit. And that information is Z2 minus Z1. So we can't get rid of anything in our potential energy term because we do have a height difference. Next up, kinetic energy. If we look at U2 minus U1, we are given some information about flow in the problem. We know that we're flowing at a rate of 0.1 cubic meters per minute. So that has to be one of these velocities, but which one is it? If we look down a couple of sentences, we see again that the liquid level in the storage tank is held constant. And if we look back at where we set 0.1, that was at the liquid level in the storage tank. Now, if that liquid level is not moving up or down, that means there is no movement of the liquid at 0.1. Even though it's flowing through the system, it's not moving at 0.1. So we can actually say U1 is equal to 0 and get rid of that term. That means that we got to have flow in the system somewhere, so there has to be flow at U2. And there is. At the entrance to the processing unit, we do have fluid coming in. So we have a velocity at U2. So that can't go away, but we can get rid of U1 because that liquid level is constant. Now let's take a look at our friction term. First, we need to write that friction term all the way out. There you have it. That's our friction term. So that first term in the friction equation, 2 times the Fanning friction factor times the velocity squared times L divided by D, that is our major friction losses. That is friction loss due to flow in the straight part of the pipe. The next 2 terms account for the friction going through our elbows and our valves. So we multiply the elbow term by 3 because we got 3 elbows. We multiply the valve term by 2 because we have 2 valves. So when we write out our entire fluid flow balance, taking out all our unneeded terms, this is what it's going to look like. And there you have it. That's our energy balance for this particular system. Notice that I said for this particular system. If something in your problem changes, we may be able to get rid of different terms. We may want to use a different term for our major friction losses. For example, if we are given a pressure drop due to flow, we would want to replace our major friction term with something else. But this is the correct setup for this problem. So that concludes this particular video. We have our pump energy equation all set up. In the next video, we'll go through, we'll figure out our flow regime, plug in all our numbers, figure out what our pump energy is, and then convert that to pump power.